Markov chains. In 1907, a Russian mathematician by the name of Andrei Andreevich Markov looked at patterns in poetry and created the first Markov chain. He used Alexander Pushkin's novel in verse Eugene Onegin to identify patterns of vowels and consonants. There are two types of Markov chains. There's discrete and continuous time Markov chains. In discrete, there are countable time sets where it's like 1 day or 2 days. In continuous, there's no set time and nothing's countable since it's dependent on many variables. Discrete Markov chains look at the probability of getting from one situation to another, like the chance of a vowel coming after a consonant. The probability is then set up into a matrix so you can compute it easier. The matrix has outcomes from 0 to 1 and can be turned into percents. In setting up a matrix, you multiply row by column of the current situation and the potential situation. You can then take the power of the matrix to figure out the probability of a situation a few steps ahead of time. Continuous time Markov chains are also known as the Markov process, since there are many variables that are unknown. It works like discrete time Markov chains, but there is no set chance of something to happen. Markov chains can be used for like weather forecasts or anything with predictive algorithms like AI. Advanced AIs use the Markov process in order to predict what will happen since like the real world has a ton of wildcards. As an example of a Markov chain, hypothetically, if a restaurant serves fries, burgers, and cokes, and a person orders a fries, there's a 50% chance that the person after them will also order a fry, 25% chance they will order a coke, or 25% chance they will order a burger. If a person orders a burger, there's a 50% chance the next person will order a burger, 30% chance the next person will order a fries, and 20% chance they will order a coke. If they order a coke, there's a 40% chance the next person will also order a coke, 25% chance they will order a fry, and 35% chance they will order a burger. You can now set that up into a table to see which the next person will order. The rows are the order of the first person since it's always row by column. You can now use that matrix to calculate what the second person will order, but you can also take the power of it to find out what the third person will order, and you can do that so on and so forth. Markov chains follow the law of large numbers, which states the more times you do something, the closer you get to expected value. That's why in this example, all the 50% chances get closer to what the other percents are, and all the low, small 0.25s get closer to the other ones also. Markov chains can have an absorbing state, where one outcome does not change for a situation. Like if someone orders something, the next person is guaranteed to order the same thing. These states have a 100% probability of the same thing reoccurring over and over again. And if it's 100% probability of something else occurring, that is not considered an absorbing state since the outcome does change. If all the outcomes have a potential to go to an absorbing state, then the matrix is considered a transition matrix for an absorbing state. If the matrix has at least one situation where it does not arrive to an absorbing state, then it is not considered a transition matrix. The matrix above contains an absorbing state with situation B, but it's technically not a transition matrix since A and C will continue to go around in circles forever. Transition matrices for an absorbing matrix can have a limiting matrix. Limiting matrices are basically the asymptotes for matrices. Now a 3-question quiz. Use the probability matrix above to answer the questions.